textbook says that a square of side x inches is cut out of each corner of an 8 by 15 inch piece of cardboard. Okay? And the sides are folded up to form an open top box. So the first thing they want us to do is write a function of the volume of the box as a function of x. Find the domain for the volume of the box of the function of x. Part C, graph V as a function of x over the domain. And then part D, how big do the cutouts need to be in order to produce the box of maximum volume? Okay. Now this is a very common ACT type problem. I see that problem all the time, and when you guys take calculus next year, that is a very common minimization, maximization type problem. So let's write down some information here. So for example number 2, what they're saying is they have a cardboard box or a cardboard sheet, a sheet of cardboard, and it's 8 inches by 15 inches. And they're not sure how much they're going to cut, but what they're saying is the height of the box is X units, right? So if I were to draw the box, the height of the box is X. Okay? Does that make sense? Now, what they're trying to do is probably they got a deal somewhere, and this is a very common type of engineering problem for businesses. There's probably a company that sells these 8 by 15 inch sheets of cardboard, and there's probably a machine that will cut the corners of the box and fold the box automatically. And so the manufacturer wants to make a box that has the maximum volume. And the problem with calculating the volume is that the volume is equal to the length times the width times the height. Well, we know that the height will equal X, but we don't know how big to make X, and we want the maximum volume of this box. So what we need to do is figure out a way algebraically to set or find the maximum volume. So if this is the size of the box, really what we're looking at is we could call this the width, we could call this the length, and then the height would be X. Well, what is the length? Well, if I unfold this box, I'm going to have something like this, right? These little corners are what I'm planning on cutting out. Well, what are the size of those little corners? Well, they're X by X, right? So, what is the width of this box? Well, the original cardboard size is 8 inches wide, but what am I subtracting from it? Huh? Not X squared, you're close though. This is X and this is X, so I'm subtracting 2X, right? I'm subtracting 2X's from it. Now I don't know what the length of X is, but that is what the width of this is. Now, what is the length of the box? Well, it's 15 from here to here, but I'm subtracting what from it? 2X. And then what is the height of the box? Huh? X. So then my volume is actually 15 minus 2X right? Times the quantity 8 minus 2x times x. Does that make sense to you guys? So now that I've written this thing, I've written the equation, the volume, as a function of x. So this is part A out of your textbook. This is what they wanted us to do first. Part B says find the domain of x. Are there any restrictions as to what x can or cannot be? Remember that domain says it's all the possible x's. What can x not be? Well, I'll tell you what the domain is, and then you tell me how I came up with that answer. Why did I say that the domain x has to be less than 4? Well, wait, can we have a negative value? No. So, x has to be greater than or equal to 0. We could write it like this. Does anybody know why?
Because we're measuring something.
Well, to some degree that answer's right, yeah? They're greater than 4 part.
Can't be greater than 4 because if you cut out a square from each side, then those would have to be, the 8 would have to be cut in.
Yeah. If I cut more than 4 inches, it won't work. Because 4 plus 4 is 8. And 8 is the shortest side of this cardboard sheet. Okay? Now the reason it can't be negative, because if we were to cut away a negative number, well, that's just not... We could do it mathematically with the equation. I'm sure there's a solution in here that might have a negative x value. But how do I plug that in the machine? I can't. So part C says graph the function of the domain and take a look at it. So if I come in here and I graph this function, and you know we could multiply it out, but we don't really need to. I could just enter it in just the way I have written it. So the equation is 15 minus 2x. So I could just plug it in the way I've written it. I could say 15 minus 2x, times 8 minus 2x times x. But now on my window, I'm going to change my domain from 0 to 4. And that's all I want to look at. Okay, I need to adjust the window a little more because it looks like the y values are a little bit bigger than I anticipated. So let's change this to 30. Well, needs to be a little more. Let's change that y max to 50. See what we got. Well, that's pretty high up there. I think we need to change the y. Let's just change it to 100 so we're not messing around with it. Okay. There we go. Got the whole thing in there. Now, if you were to guess, how would I use this information to calculate the maximum volume? Think think that through. We've written an equation that represents the volume based on the size of X. That's this thing right here. So this equation represents the volume of the box based on what number we choose for X. And I've graphed that. So as, for example, and I want you guys to look at the XY values, okay? If I choose X equals 0.25, a quarter of an inch, that means I'm going to cut a quarter of an inch out here, and a quarter of an inch out here, and a quarter of an inch out here, and a quarter of an inch out here. That gives me a volume of 27.1875 cubic inches. If I choose to cut out 0.5 inches, I get a volume of 49 cubic inches. So looking at this graph, where or how can I determine the maximum volume of the box? Yes?
I'm taking the maximum of the.
Yeah, it's real simple. We just got to look at the max of this curve, right? Somewhere up here is the maximum amount. And we could let the calculator calculate that. We've done that plenty of times. So I'm just going to hit trace, and we're going to look for the maximum value. I'm going to start a little bit over here to the left because I'm not quite sure. Hit enter. I'm going to go really far over here to the right because, again, I'm not sure. Hit enter. And then somewhere in the middle is where this thing should be. 1.66. So now what does that mean in practical terms? What did I just do? Somebody tell me. What is that 1.67? Yeah?
It's the value of X that can make the box inverted.
If that is correct. If I cut out this little square of 1.67 by 1.67 of that cardboard sheet, that will give me the maximum volume I can get. If I go a little bit bigger than that, smaller volume. If I go a little bit smaller than that, again, the volume isn't as much. This will give me the maximum volume. This is used all the time in industry. So Mr. Adams, and I don't know if you guys even realize this, but Mr. Adams is a company. We manufacture things. I manufacture tanks, rectangular tanks that hold water. So when I make this tank, I'm going to start with a sheet of aluminum. And I'm going to do this exact same process. And I'm going to cut out the four corners, and then we'll weld the joints together. And when I do this, I may have certain size requirements of what the aluminum sheets can be because I'm shipping them all over. Or the weight of the object or anything. Well, the bottom line is I may want the maximum volume of that tank based on the material that I'm using. See, I can make the holes bigger. In other words, I could cut these squares out bigger, but then my box doesn't hold as much. And I'm really wasting material. If I make the cardboard boxes smaller, the cutout smaller, well then it's not holding the same amount of material. And again, that's not being the most efficient. Now there are times in industry where people just make boxes based on the size that the box needs to be. But can you see the value and getting the maximum volume out of something? And that's what's interesting about that.